This work proposes a model for syntax recognition called Masked Vision Language Transformers, MVLT for short. I will introduce the motivation of our work, the proposed method, the experimental results, and the visualization results. Syntax recognition aims to read the text in scene images, which is challenging due to the complexity of real-world scenes. Many recent works have made progress by introducing textual semantic information, except for visual cues. The other use explicit textual semantics or implicit textual semantics. Our work further explores learning both the explicit and the implicit textual semantics. We design a network to mutually combine these two kinds of semantics. MVLT is built in an encoder-decoder architecture and trained by a pre-training stage and a fine-tuning stage. The encoder is a vision transformer, which takes image patches as input. The decoder is a multi-model transformer. To enable learning different kinds of textual semantics, we build two sub-decoders, take the image features from the encoder, and the textual part comes from the ground truth text labels of the corresponding image. In the pre-training stage, to enable learning visual features, we mask 75% of image patches, and one of the learning purposes is to rebuild the masked patches. Decoder 1 takes a partially marked text embedding as input and learns to predict the masked characters. The visible characters serve as word-level texture cues, explicitly guiding the model to learn linguistic knowledge. Decoder 2 takes a totally masked text embedding as input. The model is now left only with visual cues, and thus is pushed to learn linguistic information implicitly without any additional language model. It is worth noticing that the two sub-decoders share parameters during training for efficiency. As an extension of our MVLT, we propose a simple but efficient method to use real-world unlabeled data together with labeled ones in pre-training. We concatenate labeled and unlabeled data along the batch dimension as the input, and when computing the loss corresponding to the unlabeled data, we ignore text-related losses. In the fine-tuning stage, to better use the pre-trained knowledge, we fine-tune both the encoder and the decoder. Meanwhile, we propose an iterative correction method, which can gradually modify the predicted text during iterations. In each iteration, the input of the decoder consists of the image feature that is output from the encoder and the text feature that is output from the previous iteration. Compared to the written words, MVLT achieves state-of-the-art performance, and MVLT Star gets superior performance on all 6 test datasets. We conduct extensive evaluation experiments to explore the influence of explicit semantics, implicit semantics, and iterative correction method. The figure shows the result with different settings of the iterative time in fine-tuning and testing the model, which further suggests that the iteration correction method is very helpful. We show several visualization results of test image after pre-training the model. It suggests that the model has already acquired visual and linguistic knowledge through the pre-training stage. The figure shows a stronger model after fine-tuning, which is capable of dealing with more challenging real-world images. More examples are shown in the supplementary material. Thank you for your attention to our work. Please email us if you have any question.